I'll try to put in my perspective of what we think from Rick from the industry perspective, and where is it in terms of its maturity and its adoption uh, across various regions. If you were there last time for my lecture, we have gone through the ORAN reference architecture. So I'll quickly refresh on the two key points that I find are relevant to this discussion before we move on to understanding the RAN component, the software component of the RAN, and understanding the RIC in detail. Okay, I think Dr. Rees has covered this. So just a quick refresher on the RAN architecture. So the things that I would like to highlight is here is that in the SMO framework we have the non-real-time RIC, and the near real-time RIC is an independent component, and the non-real-time RIC is not directly connected with any of the further RAN components. It's only connected through the near real-time RIC using an A1 interface. And it's only the near real-time RIC that is connected with the CU and the DU through the E2 interface. So the CU DU is known as E2 nodes for the near real-time RIC. Okay. And then there was another point in my last lecture, which was regarding the control loops. So ORAN defines three control loops yeah, in its specification. One is the real-time control loop running at the DU, um, which is in the less than 10 milliseconds of latency considerations. Then the other one is the near real time. So near real time is between 10 milliseconds and 1 second is this loop. And then this is non-real time control loop, which is running at the non-real time link, which is of the latencies higher than 1 second. Okay, so now before understanding Rick, I would like to first take a look at how the RAN software was components are put together, and what is mean to introduce intelligence in RAN with Rick. Right. So traditionally, the RAN software has been tightly coupled with the hardware that CSPs used to buy, right? So this software had three primary components. One was the management plane, the other was control plane, and the last one was a data plane, right? So the management plane is the one that is responsible for monitoring and configuration functions for the control and data plane, right? And this is the component where we would see things like cell level statistics or subscriber level statistics. Plus, we'll also see configurations like the configurations that are used to build the RAN network. The coverage parameters, the energy parameters, neighboring parameters. Now we go one step below is the control plane. So in the control plane, we have the control algorithms that determines how the user data is processed. So on the data plane, right? So which means that is the admission control, the mobility control, the load balancing, and also things like pre-coding, PRB allocation, beamforming. Um, so those are the components that are under the control plane algorithm. So these would determine how the data would get mapped on to the air interface. And then there is the data plane, which is basically the data processing functions that transform the user data from IB packets to the UU interface, air interface components, right? So wherein all of these components are there. Right. So when we look from the software perspective, the CU and the DU have both the control plane and the data plane function, and the management plane is something that is a bit separate in the SMO or ENM component. Previously, it used to be called, right? So all of this software, until Open RAN was introduced, would be tightly coupled in a hardware in a closed box and would be shipped to the CSPs. So there was a very little scope of optimizing all of this um, components. Plus, there was no way of or no way of changing any of this, right? So if suppose a CSP find out that a vendor A's say admission control algorithm is better than vendor B's admission control algorithm, there was no way you could change that, right? Or you could replace that to have vendor A's algorithm in all of them because it used to be a tightly coupled system. Now, why was it important to disaggregate even the software component? Is because if you look it from the CSP's perspective, right, their most precious asset in the network is the spectrum, and RAN is the only component in the whole CSP's network that touches or manages that most precious asset in the CSP. Now, and how much return or how much profit you could make out of your spectrum, or how much ROI, so you can say from your spectrum you can get, completely depends on how intelligent your RAN software is. And traditionally, this has, as I mentioned, come as a box wherein both the hardware and software are tightly coupled into each other. We had very limited programmability traditionally, so there was barely anything that you could program in this. Then we had virtualization, which we talked about, right? Where we had the hardware component separate from the software component. Now the software component is separate, and you could put that software on any generic hardware platform. That is called the network function virtualization, wherein we virtualize the RAN, but the software was still tightly coupled, right? So there was still all of that software that would come bundled together, and there was very limited programmability still. However, with virtualization, you could use CTOS hardware to run those RAMs. So there was some addition benefit to that. Now with the introduction of RAN intelligence controller, even the insides of these have have been disaggregated and split into separate components. And that is why this is very important, because it is for the first time in the history of RAN. So probably from the first generation until now, it is for the first time that these inner workings of control plane can be programmed by a third party. So that's why Patrick is a very revolutionary idea in itself, and it's a great concept which is going to open up the intelligence for third parties. Now, once this software stack has been disaggregated, we have separated into various components. So there is the RAN control plane, which is primarily the near real-time rig, then the RAN data plane, which runs on the CU and DU, and then the RAN management plane, which primarily runs in the non-real-time rig. So that's how the concept of near real-time and non-real-time came into existence, because how we wanted the algorithms to be categorized or placed together. Right. So that's the background of how the RIC came into existence. Now, going back again to that reference architecture, just to highlight where all of this sits. So the RAN intelligence controller in the SMO is the non-real-time component of of the two. So it takes care of the non-real time or management plane type of functionalities, which needs greater than 1 seconds of latency. And then there is a separate component for the near real-time rig, which takes care of the control plane algorithms of the RAN, which are between say 10 milliseconds to 1 second. Okay, so this is how the rig is functionally split. So to understand then what is rig? So basically RAN, so rig is enabling intelligent control and optimization of the RAN architecture. Because until now, even though there was a lot of advancements in on the rig side, we never had intelligence that was coming to the RANs, to the RAN interface itself. So Rick introduces that intelligence to the RAN, and as you know, it splits basically it into the non-real time and the near real time. And then the non-real time rig is known as the non-real time rig, and the near real time rig has its own set of apps, and these apps are basically the algorithms that we were talking about, so the management plane algorithms on the non-real time rig and the control plane algorithms on the near real time rig are the one that you can use to now program. And these apps could be written by any third party now. So what does that mean is that you could have a Nokia RAM with say a VMware rig running say a VRV XApp and RApp. So this was not possible before. So what this will bring to the ecosystem is best of breed. So you can pick and choose the best of everything that fits your use case and your requirement to build the best of breed RAN network. And this power now lies with the CSPs, which was not there until now. So as we were talking about it, right? So what are these two forms of rig? So one is the non-real-time rig, operates on greater than 1 seconds of latency, and then the other is near real time, which is sub 1 second latency up to 10 milliseconds, right? And the way this would get deployed also is on the non-real-time rig probably would be at a centralized place. It would be connected to multiple near real-time rigs in the network. A near real-time rig would be distributed across the RAN network, and they would connect to maybe one set of non-real-time rig. So near real-time rig is something similar to what we used to have as SON or self-optimizing networks in the legacy period. And the SON has kind of been split into two again, right? So management plane again, control plane again. And the non-real-time rig also takes care of like the orchestration and management capabilities, whereas the real intelligence would come from the near real-time rig, where you would have various RAN algorithms. But all of these and these two working together through the AVER interface is what provides the IAML capabilities. I'll show you in the next slide for that. And why was a rig needed in the first place, right? So like if we have kept if we were good with not having a RAN controller with LTE, and which was a great technology, why it was needed and in the first place was because there is going to be a significant complication of deployment going forward when we started virtualizing and when you think of massive MIMO type of deployments in 5G. So the sheer number of sites that would get deployed are going to be huge in the future, just because the data demand is so high, right? And it is impossible to run it through the conventional ways of managing it very manually. We need a lot of automation there, both from the perspective of how it's get deployed and also from the perspective of how it gets managed and optimized. And that's why there is a significant need for rig as a component in the system, because it's only then that would make economical sense to deploy such huge and vast networks across geographies, right? So definitely cost saving was one of the factor. The second, as I said, right, these algorithms were never open to third parties, and that has led to um, suboptimal performances, which at the end is what we used to feel, right? So with Rick providing this ability to pick and choose between best of breed, now we would have improvement in the quality of service that would get delivered. And the third and the most important part is that with 5G coming into play and use cases like slicing and say dynamic slicing coming into discussions, we need far more automation that could manage those kind of things. And it's only with those that CSPs would be able to generate new revenue streams. And that's why a rig type component is essential in the network at this point. Right. So, as I mentioned previously, it how it comes together is that it's the near real-time that goes and talks to all the RAN components through the E2 interface, and the two rig talk to each other using the A1 interface, right? So it's the A1 interface between the non-real time and the near real time rig that from which all the communication happens, and then anything that is defined by the non-real time rig gets passed on to the near real time rig and then get implemented. But in case of so there is also a possibility that you would be able to connect the non-real time rig with the legacy RAN, which is which is not open. So in cases where there is no near real time rig, in those cases it would communicate through the SMO, so over interface. So in those cases, it was connect to the over interface to the legacy network, and would you'd still be able to use the non-real-time rig for the existing or the legacy network in this case. Okay, so let's look at what is inside these RAN intelligence controllers, right? So if you look at the non-real-time rig, so the first important thing is A1, which is coming from the near real-time rig, and there is an A1 termination here. And similarly, there's an O1 termination. O1 termination is where the O1 related services comes, and this is, as I was mentioning, this is where it would connect to the legacy network in case it has to be. Okay, and to the non-real-time rig, there are AI and ML workflow functions, which can then be made available to the near real-time rig as well. And then it has the data management and exposure functions, and even related functions. And all of this is made available to any of the apps using an interface called R1. So R1 is the interface with which the non-real-time rig would communicate with the R apps. And R apps are the smaller software components that can be developed by any third party to run on top of the non-real-time rig to enhance the RAN functionality. So previously, even if you had SON, right, which was the self-optimizing networks, you would have to have either multiple SON vendors if you want to choose between the algorithms, or you could only have, because it would mean that you would have to spend on all of them. With this, what non-real-time rig enables is that you have one common platform, and say you want a SON algorithm from Keysight and another SON algorithm from VRV and the third SON algorithm from Cohere. So all of this is possible now. You could have just one non-real-time rig, and all of this would come as apps on top of that. And this is not something that exists on slides. This is a reality today. VMware has the industry's leading rig platform, and we have more than 25 vendors who writes the apps for these rigs now. So and these are deployed in customer networks already. So wherein customers are utilizing these various app components and making most out of their RAN. Right. Okay. Yeah. There's one more thing I missed to mention is that the non-real time rig is the one that would connect to any external data sources if it is needed, right? So if you need any external data source to be included in the RAN, right, which was not possible previously, it's only through the non-real time rig that it can be done. Okay, now let's look at the near real-time rig architecture. So in near real-time rig, um, the two key components are the A1 and the E2. I think somebody was asking for why this is called northbound and this is called southbound, and so it's confusing because then for E2 nodes, E2 becomes northbound, right? So actually, that's the whole point. So when you say northbound, it is interface that is originating out of that component, and when you say southbound, it is an interface that is coming inside the component. So that's how it kind of clarifies it, and it provides you can say common platform, common terminology of how you would refer to interfaces, right? Okay, so the near real-time rig talks to the non-real-time rig on the A1 interface. Also, there's a O1 termination from the SMO side, and then there is E2 on from which it talks to all of the E2 nodes. Right. And inside that, you would see a lot of other subcomponents. So, for example, there's conflict management, subscription management, and then there is security, there's AIML, and then there are some repository functions. So, these are various functions that enables a lot of other services inside the near real-time rig. So, for example, conflict mitigation is a function that would resolve if there are two separate except that are trying to do something that would either overlap or conflict with each other, it's the conflict management's job to ensure that the RAN is not affected. So, for example, a cell is trying to turn off next app is trying to turn off a cell, and other X app is trying to turn on the cell. It is conflict management's job to ensure the right action is taken, right? And now, the subscription management is the one that provides a uniform data to these apps through the shared data layer and the database, right? The management service is kind of like the FCAPS management for this, and it produces it as a service for the SMO. Security is that we have to ensure that the XApps are not there's no leak here between the XApp, and you keep all of them separate from each other. There is also an AIML support to for these apps to be utilized, and then there are repository functions. So which means they're like common functions that these XApps can utilize to run their apps, like like policy and access control type of things. And the way these apps connect to the near real time rig is using an API. So it is the RT rig API that enables the near real time rig to connect with the X apps. In the non real time rig, it was an interface called R1. In the near real-time rig, it is the API with which they would connect with the near real-time rig. Okay, so now let's get into what can be done with this, right? So what can we use this rig for? So one is so there are a lot of use cases. I've tried to pick just a few categories. And in fact, the innovation is rapidly happening in this space. We have seen some fantastic apps being developed. In fact, there are also hackathons now that are organized to encourage new new smaller startups to write apps for the RAN. Right. So, if you look into categories, so there are a few categories to it. One is like resource assurance, wherein it would take care of, monitoring and service assurance of the RAN network. The other is intelligence, wherein you could provide AI/ML type of capabilities to the RAN. And the third is the control of the resource itself, like maybe controlling the control plane algorithms of load balancing, AMC, and handover management. So all of this you could control. You could create apps to control that. Right. So here are some of the examples that I've picked for from the apps that we have seen developed. So there are apps for traffic steering, so the which can use which are used by the non-real time rig, and they there are some that works. So they have two components of the app. One is working on the non-real time rig, and the other on the near real time, and then they work together with each other to ensure that the UVs are always spread across all the layers and avoid any congestion, and always provide the optimum performance to them. The other is that QE optimization. So if there is a lot of subscribers, you have to ensure that all of them get the best possible network experience, uh, whatever they are using the network for. So it's more like usage based optimization for these. Then there are SLAs, like their network slicing now, wherein you cut off a small part of the net layer of the spectrum, and it acts as a network independent of the rest of the network. And then you could ensure that what that network slice was created for. So it had maybe like a latency requirement, a throughput requirement that always get fulfilled irrespective of the rest of the network's load. Then there are massive MIMO optimization use cases wherein there are various algorithms that are run on the near real-time rig that optimizes where the how the massive MIMO allocation happens. There are indoor positioning use cases, which use a lot of other data sources to pinpoint the indoor locations of the UVs. This is a big monetization use case nowadays. There's congestion control, signaling storm protection, and IoT optimization. So there's so many of these use cases that are now getting developed by a lot of third-party software startups, and I believe in the coming years, this is going to be one of the greatest innovation areas in the RAN space, where you would see a lot of new startups. Even we are already seeing a lot of new startups coming up, building these apps for the RAN. So if any of you are interested, I would recommend do visit VMware's RIC site. We encourage. So we have a RIC partner program where anybody can come and learn about how to build apps. Anybody can build the apps. We provide everything that is needed for a person to build app. Even we provide a test environment, sample data, and all the SDKs are available for free. So everything is there available for free for anybody to come and develop apps on the rig. And our rig is 3GPP compliant. So once you develop an app on VMware rig, it is compliant to any ORAN and sorry, not 3GPP, ORAN compliant rig. So the app that you would develop on our rig would be compliant with any other ORAN compliant rig in the market, with minimal adaptation to it.